So in this video, I'm going to do a problem or explore a problem in front of you. So what I have is an inclined plane, and there is a block sliding down the plane. We're going to say that there is also a ruler along the plane, and this little thing is not a 5, it's an S. And S is just an amount of displacement down the plane. So S is displacement. And it's as if there is a meter stick or something lying along the plane. So as the block goes down the plane, you can just look at the meter stick and say, what is the position of the block along the plane? So the inclined plane is inclined at an angle theta. We'll say that S marks the position or displacement of the block, and the block is sliding down a rough ramp where there is friction. So this indicates we are talking about sliding or kinetic friction. And the mass of the block we'll just keep as a symbol for now. It's just lowercase m. So this is interesting. You know that if the inclined plane is very steep, we'll likely see this mass speed up as it goes down the ramp. But if the inclined plane is very shallow, then this little mass is probably going to slow down instead and come to stop or rest at some point along the ramp. So we can generically say that as the block goes down the plane, one of 3 different things can happen. And it depends on the steepness of the angle theta. So I'm going to describe a special angle theta sub star, and this is the case where the velocity or the speed of the sliding block at any position S is actually equal to the velocity of the block at any other position S, including the initial velocity of the block. So we're saying that the speed is constant. We can have the condition where the angle of inclination is bigger than this special angle. So this is one of the 3 things that can happen. Here is the next one. If we have a steep angle of inclination, then what we expect is the velocity of, say, S2 will always be bigger than the velocity at S1, where S1 is smaller than S2. That is, S2 is further down the plane than S1, for example. The speed is increasing. As the block goes down the plane, it speeds up for steep angles. For angles that are less than steep, so they are less than this special critical angle where the speed is constant, you'll instead see so if S1 and S2 are ordered the same way, so S2 is further down the plane than S1, then the velocity at S2, so we are shallow, right? The inclined plane is very not steep. We should see that the speed at further distances is less than the speed at closer distances up to a certain point. There is, in this case, some maximum position that the block will get to, such that the velocity at that maximum position will have the value 0, right? We expect the block to slow down and stop. So the speed is decreasing ultimately to some value where it stops, and it's not like it's going to bounce back up the plane, right? It's friction, just sort of deadening out the motion. Okay, so these are the 3 cases, 3 different cases. But at least to start looking at this example, I don't need to know which case I'm in, but at some point you're going to have to start thinking about which case are you in. Okay, so to continue though, it's interesting actually because I want to inspect the energy. I want to think about the energy. It's interesting to notice that here the kinetic energy is a constant, right? This is the special case of the kinetic energy being constant. In this case, the kinetic energy at further down positions will be bigger than kinetic energy at further up positions. And then this is the backwards, reverse case, that the kinetic energy of earlier positions is going to be bigger than the kinetic energy of later positions until you get to the last position where there's any motion, or so the last position the object gets to, the kinetic energy will be 0, right? Okay. So so it looks like this kind of analysis, we can use energy thinking to describe the kinetic energy as a function of location. Notice that it's not function of time. I think this is interesting. Energy kinds of thinking is the result actually of sort of getting rid of the idea of time and only paying attention to the idea of space or translation. So we can use the energy type thinking to describe the kinetic energy as a function of position, but we can also think about the gravitational potential energy as the function of the position along the plane. You notice that as S grows, the gravitational potential energy, we're getting lower and lower and lower, so we're watching the gravitational potential energy decrease as the block goes down. But also, what is the work done by the dissipative force, internal force of friction? So remember that I showed you in an earlier video that we expect that the work done by friction, the internal friction force in this system, the work done is going to remove mechanical energy from our system, and we are depending on it to have these negative values. So these negative values are going to result in causing the sum of these two values to decrease. The conservation of energy statement goes like this. It says that the change in the mechanical energy of my system is equal to, in this case, there is no external force. This is somewhat difficult to explain in a small amount of time, but let me write it anyways. This is work done by a net external force, and I'm going to exclude it because there is no work done by a net external force. As the block slides down the plane, there is no person, nothing else is influencing the motion of the block down the plane. But there is an internal dissipative work being done by friction. So I'm going to include this one. So this is you notice it's not the mechanical energy is equal to the work. It's the change. And so let me expand this a little bit and say that the mechanical energy at a further down position, an S2 that's bigger than a mechanical energy at an earlier or further up position, right? This is how the energy is changing. It's changing as I go down the plane. That's the forward in time direction. that difference between S1 and S2 is equal to the work done by this dissipative internal force, but we're going to have to include that it's the dissipative force acting from S1 over to S2. So this is our conservation of mechanical energy statement. We're saying that the mechanical energy must change if the block slides at all, because the friction force is doing this negative work that's changing the mechanical energy. So here is a very special equal sign. So this equal sign is meaningful because we are assuming that the conservation of energy statement can be written this way, or that there is in fact a conservation of energy with this dissipative internal force. Okay, so I'm going to embellish on this statement. So it says S1 to S2. I'm going to take, as I continue, I'm just going to put this as 0. That is, S1 is just the starting location. Although you can, if you want, study S1 to S2. I'm just going to study 0 to S, like this. So S2 will just be given a variable name S, like this. So it's kind of like in this situation here. So let's study for a second gravitational potential energy as a function of S. So redraw the plane. Here's the angle theta. And here is the block. That is S equals to 0. And here is the block after having moved some distance called S. And you can see, I hope you can see if I draw in pencil, that the block has descended by this much right here. So I'm going to call this H. So I'll draw over to the side. I've got this triangle where the angle is theta here, the hypotenuse is the distance S, and the height is the distance called H. And H, this is just some trigonometry of a right triangle. H is equal to S times the sine of theta. So the reason that this is interesting is because the little block is changing its location in the gravitational field. So I'm not going to embellish this too much, but what I'm going to choose is I'm going to choose that the starting point, S equals to 0, is the chosen place where the gravitational potential energy will be called 0. This gravitational potential energy down here at S is just becoming more and more negative. And so what I'm going to do is I'm going to write down the gravitational potential energy as mgh, like this, where with a minus sign. So I have mgs times the sine of theta. So theta is a fixed angle. It's not going to change. M and g are fixed values, right? We're on Earth, and that block's not gaining or losing mass. So as S grows, that is, as I go further down the plane, the potential energy shrinks or gets more and more negative. This minus sign is really important. So this is the function that is the gravitational potential energy as a function of distance down the plane, along the plane, S.